In this video, we're going to have a look at how to solve radioactivity problems. Now, this is the formula sheet that you'll be given in exams and tutorial quizzes. And you'll notice on this sheet that there are 4 equations relating to radioactivity. So we're going to look at each of these equations in turn and see how we can use them to solve radioactivity problems. It's helpful if you can print out the problem sheet which accompanies this video, because this will allow you to follow on as we go through worked examples. So the first equation on this sheet here is T half equals ln2 over K. Remember that T half is the half-life and K is the radioactive decay constant. Now it's important to remember that units must match. The units of half-life must be the inverse of the units of the radioactive decay constant. So if the units of the half-life are in seconds, the decay constant must be in inverse seconds. If the units of the half-life are in hours, the decay constant has to be in inverse hours. So let's have a look now at question 1 on the sheet. So the first question on our sheet asks us to calculate the half-life given the decay constant. So we can use the equation that we've looked at, T half equals ln2 divided by K, and we can fill in the values. It's important to keep the units in as you are working through an equation, because that allows you to work out in the final step what the units should be in your answer. So now we can enter this into the calculator. We can take ln2 divided by the K value, and that gives us this value here. Now for now we can write out the answer in full. The units of this answer will be in seconds because we've taken the inverse of inverse seconds. But the question asked us for the decay constant in hours. So we need to convert this seconds into hours. We can divide by 60 times 60, which is the number of seconds in an hour. This will cancel our seconds units and will give us our answer in hours. So now we can take our answer, divide it by 60 times 60, and that gives us this answer here. Now remember, you need to report your answers to the correct number of significant figures. In the question, we've been given 2 significant figures, so we want to report our answer to 2 significant figures. The next equation on our sheet relates A, the activity, to K, the radioactive decay constant. Now remember here that the activity and the decay constant will have the same units. They're just related by the number of nuclei, which doesn't have a unit. This N here is the number of nuclei, not the number of moles. We can now have a look at question 2, which asks us to calculate the activity of 99 grams of technetium-99. So we know that the decay constant is the same as in the previous question. So let's just copy that across. And now we're using this equation here, A equals Kn. So in order to work out A, we need to work out our value of N. We know that we have 99 grams of technetium. Technetium-99 will have a mass of exactly 99. So we can divide that by 99 grams per mole, and that tells us that we have 1 mole of technetium. But we don't need to know moles, we need to know nuclei or molecules. So we can multiply that by Avogadro's number, and that tells us that we are thinking about the activity of 6.022 by 10 to the 23 nuclei. We can now substitute this back into our original equation. So A equals 3.2 by 10 to the minus 5 per second times the number of nuclei. If we put this into our calculator, this gives us an answer here. Now remember, we need to answer to 2 significant figures because that's what we've been given in the question. So that gives us an answer of 1.9 by 10 to the 19 per second. Remember that this unit is also a becquerel, so you could also answer in becquerel rather than in reciprocal seconds. The next equation that we're going to have a look at is this third equation here, which relates the number of nuclei to the radioactive decay constant and the time that has elapsed. So let's just copy down this equation here. The first thing that we can do with this equation is use the previous equation. The previous equation told us that A, the activity, is proportional to N, the number of nuclei. So we can substitute into this equation A, where we have N. That gives us this equation here. And so we can equivalently answer questions about the ratios of number of nuclei or the ratios of activities. The other thing that you will need to be able to confidently do is convert this equation so that instead of calculating T, you calculate NT. You need to make NT the subject of the equation. So in order to do this, we need to first get rid of the natural log, and we can do this by taking an exponential of both sides. So if we take an exponential of the two sides, we get this. Now the exponential of a log cancels each other out. So now we have an equation like this. We wanted to make NT the subject of our equation, so let's just flip everything around and take the inverse of the two sides. And now we can rearrange to give us this equation. So this is an equation you may already have seen in the lectures, but it's important to note that this is related directly to this equation here, which you're given on the formula sheet. The other really important thing when looking at equations of this type is remembering which is N0 and which is NT. Now N0 is the number of nuclei at the start. Whereas NT is the number of nuclei after decay. What's crucial to remember is that after decay there will be fewer nuclei than they were at the beginning. So N0 is always greater than NT. You'll also know this because if you tried to take the natural log of a number that's less than 1, you would get a negative value. That would give you a negative time, and that doesn't make sense. So make sure you have a look at your answers to see whether they make sense, whether they are in fact positive. So the question we're going to do here is question 3, which tells us that the activity of a sample of technetium when the sample is delivered, and asked us what the activity will be after 2 days. So here in this case, this value here is our A0. That's the activity at the beginning. Over time, the activity will decrease. So we should expect that our final answer here, our AT value, will be less than our A0 value. The time that has elapsed here is in days. We need to convert that into seconds because all of the other units in this question are in seconds. We can do that easily by multiplying by the number of hours in a day and the number of seconds in an hour. So that gives us a T value here in seconds. The other thing, of course, we need to do is to use the value of K we had from our previous question. So K equals 3.2 by 10 to the negative 5 per second. Okay, so now we have all our constants. We need to work out which equation to use. We'll copy the equation from the equation sheet, replacing it though with A0 rather than N0. Remember though, we want to know AT, so we need to rearrange this equation so that AT is our subject. Let's take the exponential of both sides. Let's take the inverse of both sides. And then let's just simply rearrange. Now we're at the stage where we can replace our values into this equation. So we know the activity. Let's leave the units in to make sure we get the correct units in the final answer. And you can see it's important that we had our time in seconds so that our units in this part of the equation can cancel. We can put this into our calculator. and make sure that you're familiar with the operation of the buttons on your calculator relating to all of these questions. And that gives us this answer here. Now, of course, we need to work out how many significant figures we need. If we have a look at that, you can see in the question we had 2 significant figures, so we need to give that in the answer. So our answer is 9.5 by 10 to the 15, and the units is per second. Remember that per second is also becquerel, so here our units could be in becquerel. The last equation that we're going to look at is an equation for calculating the radiocarbon age. This is just a specific application of the previous equation. So the question we're going to look at asks us to calculate the radiocarbon age for an ancient wooden boat. The pieces of data that we're given are the activity of the wooden boat, the ancient boat, and the activity of a modern piece of wood. Now, the important thing to remember in these questions is that the activity of the modern sample is our A0. This is the activity of the carbon-14 before it has begun to decay. The activity of the ancient sample will be our AT, because this is after the sample has decayed over a period of time. And again, remember, as for the other equation, AT should always be smaller than A0, and that's a good way to check that you've calculated the correct way around. So we can now copy out our equation, the carbon-14 age, which is given by this constant times the natural log of A0 over AT. And remember that the answer for this will be in years, not in seconds. We can substitute in our values. And when we put this into the calculator, remember we now need to round to 2 significant figures. That will give us a value of 32,000 years.